So, welcome my friends, welcome to my next lecture. Now, this lecture my plan is to talk about what is called Green's theorem. In fact, coming 2 or 3 lectures, my plan is to talk about what is Green's theorem. In fact, I will give a proof of it, and then I will talk about couple of examples using Green's theorem. You can solve some of the problems. So, maybe I think within coming 2 or 3 lectures I will be able to complete these notions of Green's theorem, like the statement of Green's theorem, some proof and couple of examples. So that is the target for coming 2 or 3 lectures. So, that is the kind of title of this slides is that the Green's theorem. So, this is one of the concept, and once I done with this Green's theorem, then only 2 concepts will remain, which is like Stokes theorems and divergence theorem. Okay. So, that is what I have written. So, learning outcome of this lecture. So, what are the things I will start at the beginning? Of course, the notions of, like I have written, like simple closed curves and the orientations of closed curve and simple connected domain. So, I need those kind of concepts to talk about the statement of Green's theorem and maybe the proof. Okay. So, for that I already discussed those kind of concepts like closed curve, of course the notions of curve, simple curve, simple closed curve, orientations, simply connected domains, all kind of stuffs. If you remember at the very beginning, I have discussed all kind of concepts. So, I think I should again recall those concepts very briefly at the beginning, and then I will go for the statement of what is called Green's theorem. Okay. So, next, once I have the basic notions like the notions of curves and orientations and simply connected domain, then I think I'll discuss what is the notions, what is the statement of Green's theorem. So, I have written this the tangential form for simply connected domain. Okay. So, I have 2 types of domains you will see, one is simply connected, another one is multiply connected domain. So, I will talk about Green's theorem first on simply connected domain, and then I will tell you about the extension of Green's theorem for the multiply connected domain. Okay. So, you can do that in the simply connected domain, then you can also similar kind of statements also valid for what is called multiply connected domain with an appropriate, of course, modification. That is true. So, then of course, as a applications of Green's theorem, so I will talk about what do I mean by 2-dimensional flux integral. Okay. And of course, at the very end I will talk about Green's theorem. There is another form, first one is the tangential form, then it is the what is called normal form for corresponding to the simply connected domain. Okay. So, that is the kind of full plan for a couple of coming 2 or 3 lectures. Okay. So, first I will start with what do I mean by curve, notions of curves. Again, just to recall means very briefly I will talk about simple closed curve orientations and simply connected domains, and then I think I will talk about what is called Green's theorem for tangential form for the simply connected domain, and then I will talk about extension of Green's theorem for multiply connected domain. Then as an application you will see 2-dimensional flux integral, and then we will have at the end what is called Green's theorem, the normal form for simply connected domains. Okay. Okay. So, let us just recall once again what do I mean by curve, simple curve or simple closed curve. So, I have written that simple closed curve, sometimes it is known as what is called Jordan curve. Again, I restrict myself in 2-dimensional Euclidean space. So, I have written, so throughout our discussion we assume that the curves C are smooth curves and piecewise smooth curves or contours. Okay. So, unless and otherwise if nothing is mentioned, I will always assume that my curves is smooth or say piecewise smooth or actually the contour, if you remember. Okay. So, what is the definition? Let me just recall the definition. So, if I have a curve in R2, if you remember when I talked about say line integral, I think I have discussed once again, in fact at the very beginning when I talked about curve in Rn. So, if I have a curve in some Euclidean space, then it will have a parameterizations, right. So, therefore, a curve in C in R2, so it will have a parameterizations. Parameterizations means what? If I want to talk about curve in R2, that means there should be a map capital R which I denote it, which is a defined, which is a map from closed interval AB, but taking values in R2, and that map should be nice, right. If you remember, this is continuous or differentiable, or so that is the definition of curve. So, what I have written, so it say that, so a curve C with a parameterizations RT, and it is nice. So, let it be, if I talk about it is a differentiable curve, that means I need that what is called my parameterization should be differentiable, but at least the parameterizations I need the continuity, like if capital R is a continuous function from closed interval AB taking values in R2, then this is the corresponding parameterizations, and whatever graph you will get in R2, that is called the curve. So, that is what exactly I have written. So, a curve C in R2 with a parameterizations capital R of t. So, this is that curve with parameterizations capital R, and R is capital as a continuous functions. Then I will say that it is a simple curve. Simple curve means it should be injective, right? This 1 1. So that means R of T1 is not equal to R of T2 whenever T1 T2 belongs to an interval. Okay, I think this should be, let it be closed. It is not the open one. So T1 T2 belongs to the closed interval A to B with the fact that T1 not equal to T2, then it should implies capital R of T1 is not equal to capital R of T2. That means the parameterizations capital R is an injective. So then if a curve with the parameterizations capital R satisfies this property, then I will say that this curve is a simple curve. And what do I mean by, or okay, I have written another way, a simple curve, okay, physically you can see or geometrically you can see, a simple curve C does not cross itself. So that means you will see if I have a parameterization, so it will cannot have this kind of things, because at this point, in this point, the injectivity loss, because if I come, suppose I am starting from here, okay, so I am coming in this direction, okay, and at some point I will reach at this point, say for t is equal to t1, okay, then I will move in this direction, I will move in this direction, again I will reach the same point because there is a cross, right. So I will again reach to the same point here at some point t is equal to t2 and t1 not equal to t2, but the corresponding r of t1 is exactly equal to r of t2. Okay. So therefore I lost the injectivity if there is a cross. So that is why if I want to talk about simple curve, it does not cross itself. So that's the meaning of what is called injectiveness. That means it should be like something like that or something like that. But it should not cross. There should not be a kind of cross is there, or say figure 8 should not be there, something like that. So that means it should not be like this. It should not be like that. Okay. Because if cross like that, then at this point its injectivity loss actually. That's what I am to mean. Okay. So fine. So that means I know what is the meaning of simple curve, what is the meaning of curve, that's okay. Now what is closed curve? Again it is clear from the definitions. A curve C in R2 with I have a parameterization capital R of T, I say that it is closed. Suppose it is a parameterization capital R is a parameterization, I mean it's a continuous functions from closed interval AB to R2, because I want to talk about the curve in two-dimensional Euclidean space. Of course it is closed means that means the value of my parameterizations at the left endpoint should exactly equal to the value of my parameterization at the right endpoint. That means R of A should be exactly equal to R of B. That is called closed curve. That's exactly I have written. So a curve C in R2 with parameterizations RT is called a closed curve if R of B is exactly equal to R of B. Okay. And what is simple closed? That means it should be simple. That means it should be injective. At the same time it is closed. That means the parameterizations, it takes the value at the left endpoint. That means what it started, it should be exactly equal to the right endpoint when it's why it's end. So that means the value of R at A, it exactly same as the value of R at B. So that's exactly I have written. So a curve C in R2 is said to be closed and simple if that curve is both closed and simple. So this is called a simple closed curve, or sometimes this is called Jordan curve. So maybe in next couple of slides I will work on the Jordan curve itself. That means very nice curve. Okay. So a curve C in R2, I will say that it is a Jordan curve or simple closed curve if I have the parameterizations capital R, which is defined in some closed interval AB subset of R taking values in R2. It is simple if it is injective, it is closed if R of A is exactly equal to R of B with the domain closed interval A to B for my parameterizations R capital R of my given curve C. Okay, that is called simple closed curve, or sometimes you call this is Jordan curve. Of course, curve means what? It's a parameterization should be continuous. So that part is already there. You do not care about that. So if I talk about the curve in R2, that means I am starting with the parameterizations capital R, which is continuous from closed interval AB taking values in R2. And then next part is simple and closed. Simple means injective, closed means parameterizations take values at the left hand point and right hand point should be same. Okay, many examples are there. Okay, I have drawn couple of pictures here. For example, this is a Jordan curve. Why? Because you see, look at this picture. So this is some curve in R2. Now there is no cross, so therefore it is injective. And of course, if I start from here with some parameterizations, if I go along in these directions, at the same point, at the point, I will reach at the same point. So that means if my parameterizations are AB to R2, so this is my initial point, RA is, that means that is same as R of B. So that means this is simple closed, and of course the parameterization, the way the picture is there, it is very nice continuous function, so therefore it is the corresponding Jordan curve. This is also Jordan curve. If I have a circle, that is also Jordan curve, right? Non-Jordan curve, you see, because why it fails non-Jordan curve? It is a nice curve. This is a parameter perpendicular, and it is simple perpendicular, but it is not closed, because if I start from here, I will end up here and these two values are not same. So therefore this curve is simple, but it is not closed, so therefore it is not a Jordan curve. What about this one? This is again, it is not even simple. and also it is not closed, because if I start from here, I can go here and I can come back there, and these 2 points are different. So therefore it is not closed. At the same time it will have a cross, so that means at this point it lose the injectivity. So therefore this curve is not closed as well as it is not what is called simple. So therefore it is not a Jordan curve. What about this one? So this curve again, it's a closed curve, because if I start from some point here and if I go back, I come here and I can come back here. So that means if I have the parameterizations capital R from this to R2, that means capital R of A is exactly equal to capital R of B. That part is perfectly all right, but it will lose the what is called injectiveness. This is injectiveness, lose. So therefore this curve is closed, but it is not injective. So therefore it is not a Jordan curve. Okay. So I will work on this nice curve, what is called Jordan curve. So one example, again this very simple example. So look, I am talking about the circle of unit radius, so, and this is the corresponding parameterizations, which is cosine t first component, second component is sine of t, t runs from 0 to 2 pi. It is a simple closed and Jordan curve. Why? Because first of all it is a very nice function. So because it is a parameterization, first component is cosine, second component is sine. So it is continuous functions, because each of the component function is continuous. It is differentiable, because each of the component function is differentiable, because so therefore my parameterization is very nice. So therefore the curve is very smooth curve. Okay. And of course it is closed. Why? Because you can talk about R of 0, and if you calculate it, what is this? R of 0, this should be 1 0. And what is R of 2 pi? R of 2 pi is again cos of 2 pi, which is again a 1, and this is 0. So therefore R of 0 is exactly equal to R of 2 pi. That means this is a what is called closed curve. And of course it is simple, because you just look at the picture, which is unit circle, and it is injective, because if I take any point from 0 to 2 pi, 0 to 2 pi, if I take any point, say T1 belongs to T2 belongs to 0 to 2 pi, and T1 not equal to T2, that means because of, if I draw the picture, so for different T1 and different T2 you will have some different points. So therefore the function is what is called injective. Okay. So therefore this circle is one of the very nice example of a what is called Jordan curve. So that's exactly. Whereas you see I have written, whereas any curve of shape of number 8, now number 8 is a closed curve, but it not a simple curve. Why it is not a simple curve? Because as I said, because that this is a figure 8, na? This is kind of figure 8 kind of thing, because you lose the injectivity at this point. Okay. So therefore it is a closed curve, but it is not simple, and therefore it is not a Jordan curve, because Jordan curve is nothing but both simple and closed. It is closed, but it is not simple. Number 8. So it is a closed curve, but it is not a simple curve, and hence it is not a Jordan curve. Any curve which is not closed, that is the initial point is not the terminal point, is not a Jordan curve. Again it follows from the definition, right? If I start with a curve, if it is not closed, of course it is not a Jordan curve, because the definition of Jordan curve says that it should be simple as well as it should be closed. So therefore these are the examples of not Jordan curve. So now come to the orientation. Again I have discussed, let me just recall what do I mean by orientation of a curve. So curve I know, then I know the what is simple closed curve, that means what I know about the Jordan curve. Orientation means what? This is the definition I have written. So natural, that means if I have a curve in R2 or Rn, then parameterizations, that will have a parameterizations. If I have a curve in R2 or Rn, that will have a parameterization. And if I have the parameterization, and that parameterizations will automatically induce orientations. And that orientation I am talking about what is called natural orientations. Look, that's exactly I have written. So natural orientation of a curve, what does it mean? Means that let C be a curve. Since it is a curve, it will have a parameterization. So let C be a curve that is parameterized by capital R of t, say t runs from closed interval a to b. So therefore I will have a nice map, capital R a b to say R2 or Rn, doesn't matter which Euclidean space I want to talk about curve. Okay. So suppose C is a curve, and suppose it has a parameterizations capital R, that means it is a map from closed interval a b to that space, either R2 or Rn, whatever it is. Now look, as t increases from a to b, that means I have this interval a and I have b. So I will start from a and I will go in this direction and I will end with b. So if I is taking values, if t starts taking values from a towards b, that's exactly I am writing. So t increases from a to b, that means it's t taking value t is equal to a first and then moving towards b, that means t increases from a to b. Then of course since R is the capital R is the parameterizations, and if the parameterizations variable t which starts from A and moves towards B, then if t increases from A to B, of course the value R of t, it will follow some path in the corresponding curve in R2 or Rn. So that's exactly I have written. So as t increases from A to B, the points R of t moves continuously from Ra to Rb, because the starting point Ra, ending point is Rb. So it should move continuously from Ra to Rb in a specific directions, which we indicate that by drawing arrows along the curve. Okay. So now I think it is clear. So I have a curve in R2 or Rn, I have a parameterizations capital R. Suppose domain of the parameterization is closed interval A to B, then I will say that if I vary my t starting from A towards B, then the corresponding values R of t varies continuously on my curve in some specific directions, okay, which we indicate by drawing arrows along the curve. This direction is called what is called the orientations or natural orientations, because I am having the parameterizations and that parameterizations automatically induces a direction. So that means if I take a point t which starts from A and going towards B, then the corresponding values Rt in which direction, of course it will move along the curve in some specific directions, and that directions I am talking about is called what is called orientations or natural orientations of the curve induced by the parameterizations R of t. Okay. So for example, if I take the circle, a simple example, if I take the circle, what is the parameterizations? R from 0 to 2 pi to R2, right? So that means t goes to what? I just said this is cosine t and this is sine t. This is the parameterizations, right? Now this parameterizations automatically gives a natural orientation. So it will be a circle, not an issue. So but if I take the point, say r is equal to 0, t is equal to 0, t is equal to 0, which point it will give? So it will give, so I think this is 1, so 1 comma 0, so which point 1 comma 0, this is the 1, okay. So now if I take t runs from 0 to 2 pi, right? So this is my 0 and this is my 2 pi. So now if I starts from 0 and I am going towards 2 pi, so that means take the value t is equal to pi by 2. Anyhow, at some point of time I will cross pi by 2. Now at t is equal to pi by 2, what value you will get? Cosine of pi by 2, sine pi by 2. Sine pi by 2 is 1, cosine pi by 2 is what? 0. So therefore at t is equal to pi by 2, so therefore your corresponding, so I will write, so r of 0 is nothing but 1 comma 0, and r of pi by 2, what is the value? This should be 0 comma 1. That means I am in this point. So that means I am starting from this point, and as t runs over, as t starts from 0 and going towards 2 pi, so continuously, that means at some point of time it should cross the value t is equal to pi by 2. So that means the corresponding r of t, it moves in these directions and it will reach here. Again you go to pi, it will be this point, r of pi, because it crosses pi by 2, again it should cross pi, you will end up with this point, that means minus 1 to 0, and finally at pi means 3 pi by 2, it will cross this point, and again at 2 pi it's come back here. So that means that this is the particle. If I start with that, for t running over 0 to 2 pi, rt is a particle moves along the circle, then if t runs from 0 to 2 pi, that particle moves in these directions along the curve. So that means this parameterizations R, which is given to my curve C, which induces a natural parameterization. So that's kind of parameterization is called natural parameterizations. Okay. So this, okay, so that means if I give a circle with this parameterization, so that means the orientation is anti-clockwise. Okay. So now that is, I already talked about, given a curve, what is the meaning of negative curve. Okay, again I am just recall it, the definition. What is the meaning of opposite curve? If I have a curve, consider the curve C, suppose it will have a parameterization r of t and t runs from A to B, then you can define the meaning of opposite curve. So that I denote it as minus of C. Since minus of C is the curve, then it will have a parameterization. So if I say that, yes, look, so this is the parameterizations, then it will induce a curve, right? So therefore once I talk about the negative of that curve, that means if I talk about the parameterizations, then I am done. So that's what I am saying. So the opposite curve, which I denoted as minus of C, and what is the definition? It says that traces out the same set of points. So that means whatever in my curve, what are the points are there, so minus C also traces out the same set of points. It traces out the same set of points, but in the reverse order. That means, for example, circle, just now I have drawn the circle. So circle with my parameterizations are from 0 to 2 pi to say R2, and suppose t goes to cosine t comma sine t. So, this is a curve, this is a very Jordan curve, simple closed curve. Now, if I use this what is called parameterizations, then I just said it will take this direction, that means anti-clockwise directions. This is a curve C, right. Now, what is the curve minus C, sorry, what is the curve minus of C, this unit circle, what is the minus of C? It will traces out the same set of points, again it is the points on the circle, but this time what will happen, I will move or I will go to along the curve C in a opposite direction. That means, if these parameterizations, the usual parameterization what is given for this curve here in particular circle, it is the anti-clockwise directions. Minus C, it will traces out the same set of points, but it will be in the opposite direction, that means it should be in the clockwise directions. Now, since it will be in the clockwise directions, so of course the parameterization will change, right, and that exactly I have written, you see. So, it is given a curve C, so opposite curve denoted by minus of C, traces out the same set of points, but in the reverse order. Since it is in the reverse order, so of course parameterizations will change, and it has the parameterization capital R star. You see, I have written capital R star, which is a parameterizations of my curve minus of C, and how I defined it, it is nothing but capital R, which is the parameterizations of given curve C R of minus t, where t runs from minus b to minus a. So, therefore, if capital R, which is a map from closed interval a b to R2, and if this is a parameterizations of my given curve C, then minus C, which is the opposite curve, and what is the parameterization? Parameterization is capital R star of t, where t runs from minus b to minus a, and I can write my R star in terms of R. What is that? R star of t, which is nothing but R of minus t. Now, if I have that one, that means curve C is given, opposite curve is nothing but that, it is the same set of points, but given the curve R has a natural orientation, minus C will have the opposite one. Whatever orientation it will be there for the curve C, minus C will have the opposite orientation. If you remember my couple of last lecture, I in fact in this couple of lectures also sometimes I will show you that if I take a circle and if I have a parameterization say 0 to 2 pi, it will have a natural orientation, that means anti-clockwise. Okay. Now, if I just use the definition of opposite curve, and if I use this kind of parameterization, then you will see that parameterizations will give you the negative of my curve, and again it will be in the opposite direction. That I explicitly I will do that. Of course, in my last class I think I kind of discussed this kind of observation explicitly. That means, if C has a natural orientation, minus C will have a opposite one. Okay. So, I think this is okay. Opposite curve, definition of opposite curve, that means if given a curve C with parameterizations R, opposite curve which I denoted as minus C, which traces out the same set of points, but its order should be reverse. In other words, it has a parameterizations capital R star, which is nothing but R of minus t, this time t runs from minus b to minus a. Okay. So, once I have that one, then there is a notion called what is called Jordan curve theorem. So, that part I will come back. So, maybe later on after 1 or 2 slides I will be there, that take a circle, it will have a natural parameterizations. Then I will talk about the what is called negative of that circle. Then I will show that it will have a what is called the natural circle. If I give with parameterizations from 0 to 2 pi to R2, t goes to cosine of t comma sine t. So, it will give a natural orientation which is anti-clockwise. If I define the negative of that circle, and if I do the parameterizations R star, then I will show you explicitly that that curve is the opposite of the circle, and that time your direction will be clockwise, not the anti-clockwise. Okay. So, now come to the what is called Jordan curve theorem. I know the notions of Jordan curve. So, what is Jordan curve theorem? It says that the points on any simple closed curve, or that is same as Jordan curve C, are the boundary points of two disjoint open connected set. Is that clear? So, it says that suppose you have a Jordan curve or simple closed curve. Okay. It says that the points on any simple closed curve or Jordan curve, let it be C, are boundary points of two disjoint open and connected sets. So, therefore, I have two disjoint open connected set, and there should be a boundary, and then boundary actually what is called, there is boundary, the points on the boundary are nothing but the what is called Jordan curve. So, the points on any simple closed curve, or which is nothing but Jordan curve C, are boundary points of two disjoint open connected set. Number one of which is the interior of C, and that region is bounded, and other one is the complement, that means the exterior of C, and which is an unbounded region. For example, look at this picture, that is more clear. So, you have a complex plane, right, and suppose this is my simple closed or Jordan curve C. So, suppose this is my curve. So, okay, I am starting from here. Suppose this is my natural orientation given, with the parameterizations. So therefore this curve C, once I have curved this C in the full complex plane, then actually I can divide my complex plane into two parts. One is here outside, another is here inside. So what I am saying is that I have this domain outside, I have this domain inside. So that means I have two domain, both of them are disjoint because this is intersection with this. So this domain means what? I am talking about this interior, not included in the point C, and this is the one exterior. So therefore I have now two disjoint domain, both are open because I am taking the open one, I am not included in the what is called curve C, and of course this is connected, this is also connected by looking at the picture. And what is C? C is nothing but the boundary in between. Okay. So therefore Jordan curve theorem says that if I have a simple closed curve or Jordan curve, then it is a boundary points of two disjoint open connected sets. So this is saying, so one disjoint open connected set is this one, another disjoint connected set is the interior one, and C is the boundary. So Jordan curve theorem says that I can break my whole complex region into two parts or two disjoint open connected sets where the boundary is my simple closed curve or the Jordan curve itself. So that's exactly I have written. So and the region bounded by C, so that means this is the region, it's called, it is a bounded region. Of course it is clear from the context or the picture, this is the bounded region, that means it is the region bounded by the interior of my simple closed curve or Jordan curve. And what about the outer one? This is nothing but the complement of that, means which is the exterior of C. So this is the interior and this is called what is called the exterior. So exterior domain should be unbounded, interior should be bounded. This is one another example, right? Look. So what is my curve? My curve is, if I start from here, so it will be like that. Correct? This is my curve. So therefore if I start from here, I am going in this direction, in this direction, in this direction, and then if I go in this direction, then at least I will reach here. So therefore this is a simple closed curve, that means this is a Jordan curve. That means I can divide my whole complex plane into two parts. One is the region interior to C and one is the region exterior to C. Interior to C domain is bounded, exterior to C is unbounded. So look, the color I have given light blue. So this is the one, actually the interior one, that means this is the bounded one, and this is the white one is the outer one, that is the exterior one, that is the unbounded one. So Jordan curve theorem says that the points on any simple closed curve or Jordan curve C are boundary points of two disjoint open and connected set. So these are two examples. So once I have a Jordan curve, then you just go to the what is called the region bounded by the Jordan curve C, that means the interior region, and you have exterior region. So this is the two region which are actually disjoint, open and connected sets, and your Jordan curve is the boundary points there. Okay, so now since I talked about what is called orientations, then there is a notions of what is called positive or negative orientations of any closed curves in R2. Again, orientations means there is a convention, that means if I think, okay, let me see, then it will be more clear. So what is the definition of positive or negative orientation? What do I mean by that one? So it says that, okay, let's see, you start with a simple closed or piecewise smooth curve, simple closed smooth curve or piecewise simple closed smooth curve in R2. That means it will have a parameterization capital R. If it is smooth, means that capital R is smooth, that means it is differentiable. Okay. Then it says that if C is parameterized so that C is very nice, which is simple closed smooth curve, it will have a parameterization. Parameterization is also nice, which is also differentiable. Now if C is parameterized in such a way, that means so that the interior bounded domain of C is kept on the left as RT moves around C, then we say that C is oriented positively or counterclockwise or anticlockwise direction. So that means look at the picture, that will be very clear. Suppose this is my curve C, suppose this is C, and if I see, if I start from here and if I move in this direction, see in the left hand side you will have this bounded domain. So if these things happen, that exactly I have written. If C is parameterized so that so if I have a simple closed smooth curve by Jordan curve theorem, that means what? I can have two disjoints open connected set and boundary is that Jordan curve. So that means these two domain, one domain is the interior bounded by the Jordan curve C and another one is the exterior. So what I am saying is that given a parameterizations, if T varies, RT should varies on my curve C. Now I should vary on my curve C in such a way such that if I see the interior region bounded by my Jordan curve or simple closed curve, it should be in the left hand side. Then I will say that I am in actually a positive orientation. That exactly I have written. So, if C is parameterized so that the interior bounded domain of C is kept on the left as RT moves around C, then we say that C is oriented positively. That means, if I move in this direction, that means in the left hand side I will have always interior bounded domain. Whereas, if C is parameterized so that the interior bounded domain C is kept on the right. Now, instead of moving in this direction, suppose if I move in these directions, okay, or here I think look at here. So, if I move in these directions, then what will happen? In the right hand side I will have bounded interior bounded domain interior to C actually. So, this is my curve C. So, if I move in these directions, that means the domain which is interior of domain bounded by the curve C, which is in the right. So, if that is the case, then I will say that it is what is called negative or clockwise directions. Okay. If I move in this direction, that means I am moving anti-clockwise directions. That means this is the positive direction I am talking about. That means the interior bounded domain of C, which is in the left if I moves along the curve, and this is the opposite one. That means if I move in the right, that means in the clockwise directions along the curve C, and if I see that my what is called interior bounded domain always in the right, interior domain C is kept on the left and this time kept on the right. If this is the case, then I will say that this is negatively oriented. Okay. So, this is called what is called positive and negative orientations. Okay. So, therefore, it is quite very clear. It means if I have a simple closed smooth curve, that means it actually somehow divides your complex plane into two parts. One is the interior bounded domain of C, another one the exterior to C. So, now I will move along the curve C in such a way, if I see my interior bounded domain by C always in the left, I will say that I am actually talking about what is called positive directions or anti-clockwise directions, and if I move along the curve C in such a way, if I see my interior bounded domain always in the right, okay, then I will say that that orientation is what is called negative orientations or what is called clockwise orientation. Again, so this is just the picture I have written. So, that one is the positively oriented contour, another is the negatively oriented contour. Now, look at the arrow I have drawn, it is quite clear. That means, suppose you have a curve C which is very nice, simple closed smooth curve. That means, by Jordan curve theorem you can that curve, that points on the simple closed smooth curve or on the Jordan curve are the boundary points or two regions, two open connected sets, okay, in the region. So, one is this one, another is the light blue one, and this is the boundary one. So, now to talk about it is a positively oriented, that means if I move along my C and if I see the interior bounded domain of C which is always in the left, then I am positively oriented. Now, look, if I move in this direction, it is already given, that means in the left hand side I will have always this region. Okay. So, that means actually I am what is called positively oriented. And look at here, actually if I go in these directions, then in the right hand side I will have this what is called interior bounded domain. That means this is actually negatively oriented. That exactly I have done. So, this is positively oriented contour, this is negatively oriented contour. There is a note, of course, that note I already discussed. It says that if I have a simple closed curve C which is positively oriented, as I said, given curve C which is simple closed, it will have a parameterizations, and I choose the parameterization in such a way such that if I go along the curve C, always interior bounded domain of C always in the left hand side, that means it is positively oriented. Once I have my curve C is positively oriented, if I talk about the orientation of my negative curve minus C, it is actually negatively oriented, I already said. Number 2, if the orientations or parameterizations of a simple closed curve C is not given, suppose I just given a curve C and I did not mention anything about its orientations, then since I am talking about my curve C, it will have a parameterizations. So, then I said that then it is understood that the simple closed curve C is positively oriented. That means, if I give some curve C and if I did not mention about the orientation, by default you assume that I am talking about actually positively oriented curve. Okay. So, that means I can have a, or you can write a parameterization, or I can give you parameterization in such a way so that the interior bounded domain, if I move along the curve, it should be always in the left hand side. That means I am actually moving in the anti-clockwise directions. So, in the two examples I have given, you see that example I think I have discussed explicitly. Again you can do that. So, this is my circle, again this circle of radius 2. Okay. So, 2 cosine t and 2 sin t, t runs from 0 to 2 pi. But if I consider the negative of my circle, it will be of I think some 2 is missing, I think, yeah, this should be 2. Okay. Okay. So, minus of c, which is r star of t, which is 2 cosine t minus 2 sin t, t transform minus 2 pi to 0. This is oriented negatively. It is quite clear. Why? Because you see, what is my parameterization for minus c? If you remember, this is r star of t, which is r of minus t, and t runs from, if you remember, for r. So, this is a parameterization from 0 to 2 pi, 2 what? 2 cosine t comma 2 sin t, right, and t goes to, okay. So, what is r star t? R of minus t, and this time t should runs from where? Minus 2 pi to 0. So, that means minus 2 pi to t to 0, and what will be your map? So, this should be r of minus t. So, that means this is nothing but, if I write it, because r of t is given, so that means t times 2 cosine t, and r of minus t, that means it should be minus 2 sin t. So, this is the corresponding parameterizations of my circle C. Okay. Now, you can see, if this is my circle and t runs from 0 to 2 pi, you just draw a picture with some radius 2, that means you will see this is the 2 1. So, it will move in this direction, anti-clockwise direction, I already discussed. Okay. So, that means it is positively oriented, because if I move in these directions, the interior bounded domain always in the left hand side, that means it is positively oriented. What about minus c? Now, minus c, this will have a parameterization r star of t, which is 2 cosine t comma minus 2 sin t, and t runs from minus 2 pi to 0. Now, if I put t is equal to minus 2 pi in this here, so what will happen? So, r star of minus 2 pi, what is that value? This should be 2 cosine of minus 2 pi and then minus 2 sine of minus 2 pi, right. So, that means this is 0 and this is 1. So, that means I should be 1 0, that means I will have this here. But now you choose t is equal to, as I already explained. So, this should be, now you just 2 pi plus pi by 2. So, that means this should be what? Minus 3 pi by 2. Okay. Now, if I take t is equal to minus 3 pi by 2, you just calculate the value of r star of minus 3 pi by 2. What is that? So, this is 2 cosine of minus 3 pi by 2 and then minus 2 sine minus 3 pi by 2, right. And what is this? So, this is positive, that means this is 2 cosine of 3 pi by 2, and this is sine of minus theta minus sin theta. So, that means this should be 2 sine what is called 3 pi by 2. Okay. So, now you just use the trigonometric rule. So, therefore, this is exactly equal to 2 times cos of pi plus pi minus 3 pi by, no, pi plus pi by 2, sorry, pi plus pi by 2, then 2 sine pi plus pi by 2. What is the trigonometric rule? So, this should be plus, yes. So, 2 cos pi, so that means this should be cosine. So, look at pi plus pi by 2. So, that means I have pi plus all sine tan. So, this is negative. So, that means minus pi by 2. And what about this one? Sine, all sine tan. So, that means they can sine minus 2 sine pi by 2. But cosine of pi by 2 is 0, right? That will give you 0 comma minus 2. So, that means what? I am starting with the point 2 is equal to 0. Then, if I go from minus 2 pi, then I am taking minus 3 pi by 2. So, that means I am reaching this point. That means I am actually moving in these directions. So, earlier circle was in the anti-clockwise direction. Now, this time we will have the opposite one, that means the clockwise directions. So, therefore, if C has whatever orientation, natural orientations, this parameterization gives the, it has a what is called anti-clockwise or positive orientation it is given. So, therefore, minus of C will have a negative orientation, that means clockwise orientation. This is exactly, I think this kind of calculations I have already discussed in my last lecture as well, last lecture I should say, couple of lectures before I should say, yes. Okay. So, now I think I should stop here. So, that is about the what is called orientations. So, next class I will talk about what do I mean by what is called simply connected region. That is also I have discussed, maybe I will just recall those kind of things. So, simply connected region and multiply connected region, because I need to discuss what is called Green's theorem on a simply connected domain or multiply connected domain. So, for that this kind of notions is needed. Maybe I will start these notions I think in my next lecture. So, I think I should stop here itself. So, therefore, what we have learnt in this lecture again, so nothing new I should say, very little new. In fact, all those concepts you are familiar with in my last lectures, earlier lectures as well. So I just recall the definitions of what is curve, what is simple curve, what is simple closed curve. Maybe Jordan theorem, I think maybe this is the new for you. Okay. So then you have a Jordan curve theorem. Jordan curve means it's a simple closed curve, and then I talked about orientations, then I talked about positive orientation, negative orientations, and then the notions of what is called positive curve. Given a curve, there is a concept called negative of that curve, and then I talked about that if C has a natural orientations, whatever it is, whether clockwise or anti-clockwise, negative of C, when minus of C will have the opposite directions what is given for the C. That means if C is positively oriented, minus C is negatively oriented. If C is negatively oriented, minus of C is positively oriented. And if suppose if I give you some kind of curve, by default you should think about that curve is positively oriented. Okay. So I think I should stop here. So in my next lecture I will start with the concept called what is called simply connected region, and then I will talk about multiply connected region, and then I will go for the statement of Green's theorem and proof I will talk about. I think I should stop here now. Thank you.